Fine, started recording. Okay. Okay, so what were we doing in the last class on Wednesday? So we were doing two things. So class on Wednesday, what did we do?
Proof that comparison sort is at least of the order omega of log.
Omega and log n for comparison based sorting. Very important result. So that means you cannot do better than n log n within comparison based model. So you need to go beyond comparison based model to achieve better than n log n. And that led us to, okay, fine, that means we can do in better than n log n, but with certain restrictions. That's why we came to linear time sorting. So we said, okay, we can do it for integers. And if you know the range, what is the minimum and maximum value? If the range is, say, in order n, then we can achieve order n time sorting algorithm. That's what we discussed. And the algorithm came out to be very, very simple. So algorithm, if I repeat once, so what we said, okay, yes, I have an integer. I know the range of values. Suppose the range for simplicity is 0 to, did we say anything? From 0 to k minus 1, whatever. So there is a range. That means all values will lie within this. So what I can do, I initialize a new array of the same size as the range. So C0 to C1000. And at each index, I store how many elements in A are have the value I for I is equal to 0 to 1000. That's all. That's it. So then Ci will store number of elements in A that have the value I. So we said we can do it by simply this function 1 to n C AI plus plus. That's all. So now C stores how many elements in A have that particular value. Then have a new array or print whatever you want. And again, and just traverse this array C. And for each value, you print Ci I times. Sorry, print I Ci times. That's what you will. And that will be a sorting algorithm. And this would be order n if k is order n. This is what we did in the last class. And
So,
we said, yes.
so what if we have only two numbers? One is 1 and another is 10, say 10 lakh. Will we go on allocating 1 million, like 1 million addresses? Like, is it not memory based?
No, no, no. You see what we said. The range has to be order n, right? So you are saying if we have n is equal to 2 and the range is the 10 to the 6, of course we will not use this because the complexity is order n plus k. K is the range. So I don't want, if the range is n to n square n cube, this will be an inefficient algorithm. This will not give me order n times sorting. Only if my range is order n, then I can use this algorithm. Is that clear?
Yes, sir.
So that looked like a very simple algorithm, and I said at the end, yes, but there is one subtle point. And now let's talk about what is the subtle point. What is the settle point? So generally when we are sorting, we don't just have a simple key that we are sorting. Okay. So what happens? So generally when we have to sort, items. The items may have multiple fields. So these may have multiple fields. So think about in a spreadsheet. So you can have the name of the person, the age, maybe address, and few more things, and then let's say marks. And you keep on storing. So I'm just writing some name. Okay, let's say we are talking about two fields, name and marks. So it's a spreadsheet, some or maybe some structure where you are storing multiple fields for each item. So that is the idea. You have multiple fields. So they are all fields. And these numbers are already populated. And when you have to sort, you sort with respect to a key. Say here, suppose you're sorting as per marks. So example, marks. So you can sort them as per marks. Right? Now, when you're sorting them as per marks, fine, say lowest to highest. So you will first put Rohan, Mohan, then then Mridul, then Vishal. Right? So the question there comes, what do I do with items that have the same marks? So suppose you're sorting with respect to marks. Now question is, okay, what do you do with items that have the same value in that key?
Sir, pick up another field which distinguishes them.
So okay, so you are saying, okay, we can do one thing. Hmm, pick up another field and based on that you sort. Fair enough, we can do that. Okay, we can do that. But generally when we are sorting, we don't want to be too much troubled by other fields. Okay, so that our algorithm does not depend on, oh, what are the things in the other fields. I don't want to do that. This is a possible strategy. And actually in some of the assignment we tell you to do this. Okay, if they are having the same value, use that to define the order. Why we do that? Because so that the final answer is deterministic and we can easily compare with the answer. Okay, so that is one possibility, pick up another field. But generally what is more standard is that more standard than that is put them in the same order as they were in the input. Same order as the input, array or whatever. So that means Rohan and Mohan, they have the same marks. That means I should put Rohan before Mohan. So in this case, Rohan comes first, then Mohan, then here Mridul, and then Vishal. Very subtle point. Okay, so this is valid, but yeah, we are not doing that here. So we are doing this. Put them in the same order as they were in the input array. Why do we do that? Because you see, the original input might be based on certain things, might be already sorted based on certain criteria, and we want to preserve that. That is the so any algorithm that can ensure that any sorting algorithm that ensures that is called a stable sorting algorithm. So any sorting algorithm that ensures that is a stable sorting algorithm. So let me define that formally. What is stable sorting, and then yeah. So let me again define what is stable sorting. What is that? A sorting that ensures that for keys with the same value, the order of the keys in the output array will be the same as in the input array. It's called a stable sorting algorithm. Interesting. Is there any sorting algorithm that is not stable? Is there even a sorting algorithm that is not stable? So now forget about fields for now. So I'm saying, okay, you are given an input array. In the array, there can be multiple items with the same value. Yes. So if my algorithm ensures that they are put in the same order, it's stable, otherwise it's not. So do you have an example of an algorithm that is not stable?
Sir, doesn't this depend on how we break ties in the code we have written?
Right, right. It depends on that. How do we do tie breaking the code? But see, many algorithms you can ensure that tie breaking you take the first one always. Then let's say in the case of tie, you take the first one in the input array. Then
Sir, it will depend something like if whether we write greater than equal to or greater than, right? Mostly.
Sir, I think in quicksort it is not possible.
yeah. So quicksort is one algorithm that is not stable for sure. Quicksort is not stable. Why you do swaps? You do a
Sir,
lot
merge
of
sort also.
merge sort.
Yes,
Are
sir.
you sure?
No, sir. Merge sort we can modify.
Because we can ensure, because we are merge sort, we can ensure this is stable. But quicksort we cannot because there are too many swaps. So, and yeah.
So heap sort.
Heap sort.
Sir, in that I think we can ensure like we insert from starting. So we can ensure, and when the equal, then we keep the first node at the top.
Yeah, so there is some way you can ensure, maybe. So heap sort, we have to think, but in quick sort, you cannot. Quick sort is not stable, for sure. So anyway, I think try to think about all the algorithms. Maybe towards the end today we can discuss in detail about the 5 algorithms we talked about. Which one is stable, which one is not. But you see, at least there's one algorithm that is not stable. Okay. So then why I'm talking about stable sorting? Because we want to use counting sort such that this is stable. Okay. So now we are saying okay. So I want to do counting sort, but I want a stable sorting. That means if in A there are multiple items with the same value, they should be in the same order. Now tell me, the algorithm that I wrote here, was that stable? Yes and no. Because you see, I didn't even care about elements having multiple fields. I said, okay, if I'll print ICI times. I'm just printing it again and again, right? I'm printing ICI times. So I don't know which one is coming first, which one is coming later. So I need to have some notion of ordering in the input, and that can come via maybe putting another field with the elements. And let's try that. I want a stable sorting with the counting sort, and let's see whether we can do that. So what is our input? So you have an array of n elements, and suppose they have multiple fields. And they need to be sorted with respect to one field, right? Need to be sorted with respect to one field. And say that is key. Okay. And also, and assume that the values in key lie between 0 to k minus 1. And k is order n. So that only just to ensure we can, the values are all integers. And k is order, so that we can apply counting sort. So let me give you the input array, and then let's see how we will apply counting sort. So I'm putting some values. So 2 fields, key and another field, say something, it stands for something. 1A, maybe the name starts with this letter. 2B, 0B, 1B, 0C, 0D. Okay, I'll come from here. 0K, 0M, 0P, 2R, 2S, 1S, 0S. So there are 13 elements. 13 elements. And the key ranges from 0 to 2. Okay, so of course k is order n, range is order n. I want to apply stable sorting, and actually I want to do counting sort.
So we use linked list.
Linked list.
Array of linked lists.
Array of linked list. Yeah, if there was an array of linked list, we could have done a lab with that. Yeah, just joking, but Uh-huh. So you are saying, okay, the range is from 0 to k minus 1 or whatever, 0 to k. I will use k linked list.
Yes, sir. So that we can store the indexes of the same element, I mean elements with same keys in an order. So we can preserve the original order and we can sort using counting.
Okay, so there is one solution using array of linked lists. Arrays of linked list. And each linked list will contain one key, all the elements, and they will be sorted in the input order. They will be in the input order. Okay. Fine. I want something simpler. Okay, will work. I want something simpler. Can I not use the previous algorithm that I just described on that testing? Let's start. Okay, let's start using that algorithm. See where we find difficulty. Okay, so let's reuse our algorithm. If this doesn't work, I'll come back to this. So what we will do, so we have an array A. So initialize an array C for counting of size k. Size k. Okay. So C will stores how many times? So Ci stores number of times I appears in A, right? So what will be array C? How many times 0 occurs? 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3, and then 2 will also be 3, there are 13. Very simple. I do a single pass over A, I can fill this array C. Good. Now that's where the trouble starts. Suppose I want to output everything in array B. Suppose we want to output in array B. So this algorithm, my algorithm told me that, oh, you print 0 7 times. Or that means what I will do, I'll put 0 7 times. But now 0 is not alone. 0 is coming with all the other fields. There can be multiple fields. So suppose I just want to use my algorithm, what will I do? I will say, okay, okay, fine. I have the array B. I have to print 0 7 times. I don't know what are the fields. So what I will do, I'll go from here, find out wherever I find 0. I'll print this. Okay, 0 becomes here. Then next 0C, 0D, wherever there's 0, I fill here. Same thing I do with 1, I do with 2. Is that a good algorithm?
Sir, it will be of order k.
Right. So I can do like that. I can say, okay, first make a pass through A for each j in 0 to k minus 1. And fill that in B. You know, this will work, this will give me stable, but this will be order kn. No, I don't want that. K is order n, so this will be order n square. Why do I need to have a n square algorithm just for ensuring stability? Right? I want an order n algorithm. No, this is very bad. This is very bad. Yes, so what can I do?
Sir, we know that 7 elements will be 0, right?
Yes.
So we can assign first 7 positions to 0, next 3
Yes.
to 1, and next 3 to 2. And when
Yes.
we traverse array A once, and we can maintain 3 pointers, like which region we have filled how much. And we
Very
can
good. Very good. Very good. Mhm. Very good. I think now some of you might be getting that idea. So what I know, okay, let's think again. When I traverse A, I'll either find a 1 or 2 or 0. I cannot find anything else. Yes? Suppose whenever I encounter an element, I know what is the position B I should put it in. I am done. Then I have to make a single pass through the array A and I can fill B. If I know what is the position B in which this element should come. And this is stable sorting, this should come in the first available position in B that is available for A. Right? So, okay, what is the position in B it will come into? Which position in B this element will go into?
Index 7 or 8th position.
Index 7. Yeah, let's say zero-based indexing, it will be index 7. Okay, so this will go into index 7. Okay, where will this go?
Index 0.
Index 10.
Index 10.
Index 10.
Okay.
And where will this go?
0.
Index 2. Now where will this go?
8.
8.
Exactly. Now you can see it's easy.
So,
Yes.
but even for moving the pointer, we need some order and steps. Right? Like
No, so I
after
will
the
not use a
second.
pointer. I will not use a pointer. I said his idea was good, but I will not use a pointer. Okay, I don't want to use a pointer. Okay, so what will I do? Okay, so good. So you got the idea. Now let's see how exactly we will do this. Okay. So idea would be, see your C initially is storing, Ci is storing how many times I appears in the input array A. Okay. That's all. Now you don't need to have C as it is. So I just modify C such that CI stores what do you want it to store?
So the
Indexes.
index.
What is the index in B where the next element in A with value I go to. It's a complicated sentence, but you see what I want C to store. At any CI, this will store, okay, I corresponds to the value I, right? Say 0. So it will store, if I encounter next 0 in A, what will be the index in B it will go to? That's all. So in the beginning, what should be C? So what is the initial C? What should be the ideal C in the beginning? Ideal C in the beginning. Forget how we will get there, but what is the ideal C? That follows this definition.
Sum of C0 to Ci minus 1.
No. I want the actual value of C. Initial.
0, 7, 10.
Good. 0, 7, 10. Because the first time you encounter 0, it should go to 0 index in B. First time you encounter 1, it should go to 7. And first time you encounter 2, it should go to 10. Right? So this is the ideal C. And the C should change. C should change as I keep on traversing array. So how will I get from the initial C to this ideal C?
Sir, cumulative sum.
So, okay. So I have to go from 7, 3, 3, 2, 0, 7, 10. So I do that in 2 steps. Step 1, shift right. Shift right by 1 position. What is the formula for that? C hedge elements from 0 to k minus 1. What is the formula? I mean the actual programming code.
So for I equal to k minus 1, I is greater than 0, I minus minus. Sir, Ci equal to
Ci minus 1.
Ci minus 1.
Good. You have to go backwards. You have to go backwards, right? And then after you are done, you say C0 is equal to 0. Sure? So this is step 1. So shift right. So what will happen after step 1? You will get 0, 7, 3. That is the output. Next will be cumulative sum. Step 2. Cumulative sum. Yes, here for I is equal to 1, I less than k, I plus plus, Ci
equal to Ci plus Ci minus 1.
and this should be sufficient. And this would give you this output.
Yes, sir.
0, 7, 10. Okay. And you see both steps are order k steps. They both take order k times. Both of these. So that means I started from the counting array that I did Wednesday, and from there I can transform to another array that stores. So Ci now, again you see the definition if anybody has a doubt. Ci stores where will the next element in A with value I go to in B. Okay. So next element with 0 will go to index 0, 1 will go to 7, 2 will go to 10. So this is the initial C. Then what you have to do is very simple. So as you traverse A, so when we traverse A, if we find a value I, after you have put that in B, increment Ci.
I will increase Ci by 1.
That's all. You increment Ci. After this has been copied, Ci plus plus. That's all. That's all you have to do. Okay, so let's quickly check. Okay, I will write those values again very quickly, and then we will see how they will go. 1A, 2B, 0B, 1B, 0C, 0D, 0K, 0M, 0P, 2R, 2S, 1S, 0. 13 values. And my B is again size 13. 10, 11, 12. Yeah, 12. That's it. Okay. And my C 0, 7, 10. 0, 7, 10. There's my A. My B and C is 0, 7, 10. Okay, let's do quickly. I am traversing A. 1A, I'll see, okay, what is the value at C of 1? 7. So I put that at index 7 here. So this gets value 1A. Okay. And I increment this by 1. So this becomes 8 now. That's it. 2B, okay, where is 2? Index 10, put it at 10. 2B and increment by 1. So this becomes 11. 0B, index 0, increment by 1. 1B, index 8, increment by 1. 0C, index 1. 0D, index 2. 0K, index 3. 0M, index 4. 0P, index 5. 2R, index 11. Index 11, so 2R comes here. 2S, index 12. 1S, index 9. 0S, index 6. Okay, so my array B is done. And you can observe that we only did order and steps. Order and steps while we traversed through it. We looked into C. We found out the index in B where this will go to. I put the value, increment C. Is that algorithm very clear?
Yes, sir.
Okay. So that's the stable counting sort. Stable counting sort. Order n plus k gives you stable sorting algorithm. Is that in place? Is that an in place sorting algorithm?
No, sir.
No. For
No,
in
sir.
place sorting algorithm, you should use only order 1 extra memory. Order 1 extra memory means only finite number of variables. Should not use an array of the same size. Okay, like here, for example, you are initializing 2 arrays, C of size k, k can be order n, also B, you want to put output in another array B. So you're not doing in the 8 cell, so you are actually initializing 2 arrays. Okay, so that is, you're using order n extra memory. This is not in place. Very good. Okay, let's try something more. So till now we can do integer sorting when the range is order n. What, suppose somebody says, okay, so what? Suppose I have n integers, but the range is from 0 to k minus 1 and k is order n square. Then what will you do? Can you still get an order n log n algorithm? Sorry, order n algorithm. Can you still get an order n algorithm? Let's say stable algorithm. What do you say?
No, sir.
Anybody else? Oh, answer appears to be yes. Yes. And interestingly, reuse the same ideas. Reuse the same ideas. Oh. Reuse the same ideas we have talked about. No new idea.
Sir, we can sort it first using the remainder left by division on n, and then the quotient on, and then sort using the quotient on division by n.
Good, good. So what we can do? So suppose k is order n square. Okay. So what we can do? So now my A is an array of n integers, range 0 to n square minus 1. That's k is n square. Okay, so what you can do, fine. So each integer a can be written as a1 times n plus a0, where what is a1? A divided by n, you take the floor, and a0 is a percentage or whatever, a remainder n, the way you call it. Is that correct? I can always write a as this. Is the equation correct?
Yes, sir.
Right? So I divide by n, and whatever I get, that is a1 times n plus a0. Good. Now I know that both a0 and a1, they are in 0 to n minus 1. They both have a range from 0 to n minus 1. Then you say, oh yes, so then I have both a0 and a1 in the same range of order n. Now let's call this. So then I can write each element a as a1, a0, and a0 is the least significant bit, and this is the most significant bit, right? I can write like that. So now how can I sort all the elements? To sort all the integers, what can you do?
So first sort according to A1.
Sort according to a1. Okay, I'm just writing.
And then if they are equal, then sort according to A0.
If they are equal, then sort according to a0. Okay.
Means suppose we have 5n plus 3 and 5n plus 4.
You see, but it may happen. But yeah, this will be a complicated thing. You're saying sort according to a1. If you find things that are equal, you sort them as per a0. So how? Yeah, you have to first accumulate all the things that are. Can you think of something simpler?
Sort
Just
according
work
to
this will be
A1, 0, then A1.
Yeah, that would be the simpler one. So first you sort according to a0. Use counting sort. Okay, then LSB. Sort is per LSB. Then next step.
Sort according
Sort
to
according to a1.
That's all. Again counting sort. So use counting sort twice. First as per a0, sorted, stable, and this is stable, right? So once in the second step you will sort as per a1. If two values have the same a1, I mean same MSB, this will be put in the same order as the input. So what will happen? They will already be sorted because I've already sorted as per LSB. So this will work. If I reverse the order, will it still work? What if I reverse it? First sort as per a1 and then as per a0. Will it still work?
No, sir.
No.
So we can send slices of array inside the function according to which size contain which A1.
Yeah, so what will happen? Something like, say something like 77, and there is something like 30. So in this case, because you're later sorting by LSP, 30 will come before, or no, I should say the other way around, 70 and 37. So because you're later sorting by A0, 37 will come. 70 will come before 37. 70 will come before 37 because 0 comes before 7. So this will not, but this will. Okay, let's quickly do an example so that you are convinced. If anybody has not.
Sir,
Yes.
what is n here? Means in sorting A1 and A0, we need to specify n, right? Because A1 is quotient on dividing by n and A0 is the remainder.
See, n, we said n is the number of elements that in there.
Okay, so here n is 2,
We are
right?
saying suppose the range is, see what we are saying the setting is this. So we have n elements and ranges from 0 to n square minus 1. That is the setting.
Okay, sir.
So okay, I'm giving you some 10 just to keep it simple. Because if I use n equal to 10, I don't have to do this percentage and all separately. So let's take n equal to 10 example. So decimal itself takes care of this. So range is from 0 to 99. So 52, 33, 07, 41, 62, 27, 75, 17, 47, 30. Now, first sort as per, this is your A1, this is your A0. So sort as per A0. So what will come first? So 0. So there is 30. Then anything with 1, there is 41. Anything with 2, 52, then 62 in the same order. Then there is 33, 33. Any 4, no 4. 5, 75. 6, there is no 6. 7, yes, 07, 27, 17, 47. Anything with 8? I'm done. Yeah, that's all. So this is sorting as per A0. Now you do stable sorting with A1. So now you only see this. Okay, so what is the lowest one? 0. So the same order, so 0, 7. Anything with 1? Yes, 1, 7. Anything with 2? 2, 7. With 3, 3, 0, 3, 3. With 4, 4, 1, 4, 7. With 5, 5, 2. Yes, with 6, 6, 2, 7, 7, 5. 4, 5, 6, 7. Yeah, and you see they are sorted. Okay, so what is the complexity? What is the complexity?
Order n.
So you are running counting sort twice. So order n plus k, and k is order n, so that is order n. K is order n. Now can you see, oh, this is good? So then I can generalize that, right? So if you generalize this idea, if my range is n to the power d, and d is in constant integer,
Sir, it will not be order n.
What will this be?
Sir,
Order
it
D
will,
and
Yes. So then you have to use counting sort D time. So complexity will be order D times n plus k. And k we have taken order n, that is order dn. Order d. Okay. So as long as these are constant things like 2, 3, you don't care so much. But if d starts becoming large, comparable to log n, then it is not useful. Right? So as long as d is small compared to log n, this is fine. But in general, you can use it for input that is changing from 0 to n to the power d. Yeah. But yeah, just the catch, d should not start becoming log n. Then you don't gain too much. And this algorithm is called radix sort. So because you're computing the remainders and you're computing radix, and that is how you're sorting. But this is nothing but applying counting sort multiple times. Okay.
sir, if d is order log n, then also we can use this sort, right? I mean,
You can always use that. That's not a problem. I mean, you can use it. I can say, yeah, comparable to. Let me write it comparable to. Log n is fine. And generally, that's what we assume. Log n is quite large. So you can use that.
Sir, in the previous slide, means first we sorted with respect to A0,
Yeah.
and then means when we sort with respect to A1, we run counting sort on the means new sorted array, right? Means
Yes,
the
of course.
and
This is
then
the-
order is maintained as per initial order, means
as
stable
for
sort.
this order,
Okay, sir.
initial order is gone for you. Now you are doing only this part.
So space means we are doing in place, right?
No, it's not in place. We said that it's not in place anymore.
So each time we have to initialize new array and then do it.
Yeah, of course, you can reuse this array to output. Things are like if you have to manage your memory, you can do things like those. Okay, because this is no more needed. Once you go from here to here, this is no more needed. Okay, so you may want to reuse this array for outputting. That's a separate thing. I don't know how this will work, but maybe you can do that.
Okay, sir.
At least for 2, this is easy. Recursive code, I don't know, but at least for 2, this will be easy. You have to just output here. And now, if you don't mind having another array, you initialize another array. So counting sort once from here to here, then from here to here. That is what you are doing.
Sir, what will be the parameter when we get k to be order n to the power d and d is greater than 2? Because here are two parameters, we get the quotient and the remainder, but when we get n to n cube, then how will we split on the base?
No, and you see, this will be three things, right? So just take n is equal to 10, right? So can you not write 999 as 999? Yes, 9 into 10 to the power square plus 9 into 10 to the 1 plus 9.
Okay, I got it.
So this will be n to the power d minus 1, n to the power d minus 2 up to, So, okay, so two simple ideas with very good ideas, counting sort, radix sort. They both work in roughly order n, and this works in order dn, just to be precise. But we take d small so that this is also order n. D is a constant for us. So this is also order. There's another algorithm that does something similar, and that is not restricted to integers. Okay, so I'll just give you the idea. Another algorithm that can go beyond integers. Okay, but this gives you complexity expected order n. Now, as soon as you say expected, what comes to your mind?
The randomized algorithm.
Anything else?
Average time complex.
Huh?
Average time complex.
Okay. Yeah. So that means this is expected. On an average, this will happen, but worst case can be bad. So what will happen in this case? Expected is order n, but worst case can be O of n squared. What is that algorithm? This is called bucket sort. What this will do? So take your input. This can be anything, it need not be integers. Okay, take your input. Okay, and it is coming from some distribution. So if you can somehow find out, so there are n elements. If you can somehow divide your input into n buckets such that each bucket is expected to have order 1 elements. So suppose you can divide your input into n buckets. So example, I'll give, suppose you have integers, and you divide them, okay, starting from 0, starting from 1, starting from 2, up to starting from 9. From 0, starting from 1, 2, 3, 4, 5, 6, 7, 8, 9. These are your 10 buckets. Let's say these are your 10 buckets. Okay. So anything that comes, suppose you get, what will be starting from 0? Yeah. Yes. Huh. Let me remove 0. Yeah, starting from 0 may be only 0. Fine. Take any integer, say 15, you get 15, it will come here. Like that. 32 will come here. So suppose you can divide into some n buckets, and each bucket is expected to get order n 1 elements. Then what can you do? So you have a function that maps input to these buckets. Map it to these buckets. Now sort each bucket individually. And now one very important point, you should be able to just concatenate the outputs to get the final output. Concatenate. That will not happen here, right? That will not happen here. So my buckets were wrong. Yeah. So concatenate the outputs to get the final output. So in this case, my bucket should have been wrong. Let me just remove this. So something like, suppose, better would be, suppose your range is from say 0 to 1000. You can have 10 buckets, say 0 to 100, 101 to 200, and say 901 to 1000. 10 buckets. And you put elements in each bucket, you sort individually, and then you can concatenate. Then you can just concatenate the outputs. Okay? Sort individually and concatenate. and this is bucket sort. Just a very simple idea, but you can see this is only expected order n because you are assuming that each bucket, assumption is each bucket will get order one element, but it may happen all elements go into the same bucket, right? So in the worst case, you have to sort each bucket, and for sorting, you may use a very simple algorithm like insertion sort or whatever. So that can be order n square. But of course, if you use n log n algorithm, this will be n log n. This will be n log n in the worst case. So worst case complexity will depend on how you are sorting individual bucket.
Sir, what is the size of each bucket will we take?
Each bucket, you won't take the size. Here you can take things like linked list. You can use a linked list for each bucket.
But sorting those linked list will be tougher, right?
Okay, sure.
We cannot use merge sort.
Yeah, cool. So that is why I think linked list, and then you have to use insertion sort, so that will be order n square in worst case. Yeah. So you have to use linked list, something like a linked list, and then you have to use an order n square algorithm for sorting. Yeah. So in the worst case, that will be bad, but on an average case, there will be constant elements per bucket, and you will not worry about using order n square per bucket. So that is the idea. Expected order n.
Sir, can we use 2D array?
See, you can use 2D array, but you have to have the size. You have to initialize the size as, I think, and this number of buckets time the number of elements, right?
Yes, sir.
There's too much memory wastage maybe, but you can use that. See, idea is that if you have to worry about worst case, that's not a good algorithm. That's the thing. But you say, okay, in average case, that will give me order n. That's all. In the worst case, that is bad. Worst case on log n, you have better algorithms. You can go for merge sort directly. Merge sort gives you order n log n in the worst case. So yeah, only if you are, you are excited about the expected case. Okay, fine. Expected case, this will give me order n. Let me go for that. Fine, you can. But worst case, there is no guarantee. That's it.
Sir, what is the number of buckets? I mean, is it order n or some?
Order n. Order n. That is sorting. There are order n buckets. And each bucket has order one element. So that is why sorting will take again order one time per bucket. And you concatenate order n times, you have the final output. But the catch is order one element per bucket. Okay, that may vary. Is that okay? I'm not going into much detail of this, but just a bit of idea. So fine, if that is okay, Prashant, are you there? We should start the tutorial.
Yes, sir, I'm here. I'm
So
starting.
I'm making you a presenter.
Okay, sir.
Just a second. Can you please see that you can share your screen?
Okay, sir. I'm sharing my screen. Is my screen visible right now?
Yes, I can see your screen.
Okay.
Okay, then Prashanta, over to you.
Okay, thank you, sir. So, good afternoon, everyone. Today we shall discuss about a problem on hashing, and my name is Prashanta Datta. So let's begin. So I have just decided the content should be like this. First, we shall discuss a problem of the previous year, and then we shall see some examples of that problem, and finally we shall discuss about the solution, and finally we shall discuss the implementation. of the solution. So we transaction called trades every day.
Sir, you are
Yeah.
not audible.
They're not audible,
Sir, your
right?
voice is cracking.
My voice is cracking. Now, is it cracking now? Hello? Is it
Yes, sir, it is
still
fine now.
Is it fine? Okay. Thank you. So what I'm saying that I'm discussing the problem actually. So the problem is X is a certain company which operates in stock market and they enter a huge number of financial transactions called trades every day. On other side of each trade, there is some company Y, call it counterparty of X. Okay. So to each trade of X is assigned a portfolio number, which is not a unique identifier of the trade. That is not even unique per counterparty. In other words, the trade with different counterparties may be assigned the same portfolio, and different trades with the same counterparty may be assigned distinct portfolios as well, according to some internal policy of the company. So whenever X enters into a trade, a line such as plus 10126 is appended to a log file where plus indicates that a new trade was initiated by X and 101 is the counterparty ID, 26 is the portfolio of the trade. At any time during a typical day, however, a counterparty Y
Sir, it is breaking
Sir, you're
again.
not audible, sir.
oh, now still it is breaking, right? I'm not audible?
Yes, sir.
Audible or not audible?
Sir, you are not properly audible, sir.
Maybe it is some internet issue. Let me check. So can you kindly read the problem from here? I'm giving you a few seconds for that. So okay, the problem is like that. X is a company and Y is the counterparty of X. And when Y is doing a trade with X, we get a lock like this, plus 10126. So here 101 denotes the counterparty ID and 26 denotes the portfolio number. Okay. And at any time of the day, Y may withdraw all the transaction that was done with X. And in that case, the log will have an entry like minus 101. So minus indicates the cancellation of the transaction and 101 is the counterparty ID. So is the problem clear? Can anyone answer? Hello?
Yes,
Yes,
sir.
sir, the problem is clear.
Okay, okay. Then can you answer me one thing? Which one is unique? Means whether the counterparty ID is unique or the portfolio ID is unique or no one is unique or both are unique. Which one is true?
Sir, counterparty ID is unique.
And what about portfolio ID?
So it is not unique.
Yeah, that is true. So counterparty ID is unique, but portfolio ID is not unique. Okay, now the objective is that by the end of the day, you have to find out the distinct portfolios associated to all the transactions. Okay? So you have to find an efficient solution to this using hashing and print the hash tables. Okay. So, but there are some conditions. The condition is that the hashing function is simple mod function, and you can use if k is the key, then the hash function could be k modulo the size of the hash table. And if there is any collision, then it should be avoided using separate chain. So we shall keep a linked list for each entry in the hash table, and when there is a collision, we shall add to the last position of the list or to the first position of the list. And another thing is that you may use the following definition to define the hash structure. Okay, so the hashing may have the key and the pointer to the next node. So the log file will look like this. So here you can see that there are multiple transactions in a day. So plus denotes the transaction happened, and minus denotes that all transaction which was done previous to that was cancelled by that particular counterparty. So can you tell me what will be the answer in that case? Means in this case, what should be our answer?
Sir, answer means
Is
the
it
hash
4?
table, right?
You can say that unique portfolio numbers. That is our answer, right?
Sir, is it 4?
No, 4 is not answer, because
Okay.
here we want the, if you see the objective, we have to find the distinct portfolio numbers, right? So we need the distinct portfolio numbers with the transactions. 4 is correct because 4 transactions will only be there after the end, at the end of the day. But the answer should be kind of, see, here these 4 trading was done, and after that we got minus 101. That means all the trade which was done by the counterparty 101 is gone. So these 2 entries gone. Similarly, at the end of the day, you will see that minus 2 is there. So all the transaction which was done by the counterparty previously, that is also gone. So that means 2 is also gone. Okay. So remaining things are this entry and these 3 entry. Right. So the portfolios are 4550, 26, 184 and 4550. So if we take the unique portfolio numbers, that is 26, 184 and 4550. Right? Is it clear?
Yes, sir.
That will be the solution. Now the input format which is given is like this. The first line will be the hash table size which will be given to you, and second line contains one integer, that is the number of test cases. So test cases means the number of transaction in that particular day. So if you see that there are total 9 transactions, so that's why it is 9. And in each transaction, if we see the first column, that is plus or minus, that means whether the transaction happened or it was cancelled. And this column indicates the counterparty ID, and this column indicates the portfolio numbers. Now here you can observe this thing that when we are doing the minus, we are just giving the counterparty ID. We are not giving any portfolio numbers, because when we are doing some minus operation, that means all the portfolios to the particular counterparties are deleted. So that's why we are giving only minus 45. Now the solution. The solution could be 2 mirroring hashing. So let's see what is that. So here basic level solution could be like this. You will have to implement 2 hash maps. One is by portfolio hash map, one is by counterparty hash map. And the keys in the portfolio hash map, if we see, the key are the portfolio numbers and the values are the counterparty's ID. And similarly, by the counterparty hash map, keys are the counterparty's ID and values are the portfolio ID. Okay, so we need these 2 hash maps. And the visual demonstration could be like this. So here you can see this is by portfolio hash map. So here all the keys, so these are the keys and these are the values, similar to this one also. These are the keys, these are all the values. And here the keys are the portfolio numbers. So these are all portfolio numbers, and these are basically values which are the counterparty's ID. And it is just the opposite. So here the keys are the counterparty's IDs and values are the portfolio numbers. Okay, so the output format which is required is like this. So first column denotes the table type, means you not only have to give the unique portfolio numbers, but you have to print the hash table at the end. So the printing should be like this. So first column should be the table type, whether it is by portfolio or whether it is by counterparty. If it is by portfolio, then it is P. If it is by counterparty, then it is by C. And second one is the index of the particular hash map. Okay, so there are total 7 lines in the hash map. So that's why 0, 1, 2, 3, 4, 5, 6. So 7 unique values are there. And this column denotes the keys and this column denotes the values. So for in case of, if we are talking about the by portfolio hash map, the keys are the portfolio numbers and values are the counterparty's ID, and the reverse is true for this one. And when there is no note with associated with a particular portfolio number or associated with a particular counterparty ID, then we shall just write -1 and -1. Okay, the output format is clear.
So 2 is coming twice, P2.
Yeah, that is because in this table we have two entry. Okay, in the index position of 2 in the hash map, we have two entry. One is 56, another is 55. So this is by portfolio. So 23 is the portfolio ID, and two counterparties did the transaction. One is 56, another is 55. That's why it is coming twice. Like this, if you see the visual representation, this is by portfolio, right? For a particular, say this, we got two entries, right? So we have to print this one and this one. That's why it is coming twice.
Sir, the order matters.
Which order you are talking about?
Sir, the third and fourth lines, P2 2356 and P2 2355, can be printed in the other way also.
Actually, order matters somewhat, because actually what we're doing, when we are inserting some new element in this hash table, what we're doing, we are inserting to the beginning of the list. If you are getting this kind of means, if you are assuming this, then you will get a unique order. So order will not be different. And if you always add to the last of the linked list, then the order will be different. But in that case, we have to traverse to the last. So it will be better if we just add the list in the beginning of the linked list. And in that case, order will be always same.
Okay, sir.
Any more question regarding the output format? Or anything else? Okay. So the algorithm, now think about the algorithm. What to do with the algorithm? The log file is traversed from top to down. Okay. So for each line with a plus sign, we inserting the key value into the two hash maps. So we have two hash maps. One is by portfolio, one is by counterparty, and we are inserting based on that what will the key and value that we are inserting. So here I'm writing key value because the key value are different for two different hash maps. Okay. And similarly, for each line with the minus sign, we are deleting the key value from the two hash maps. The algorithm is very simple. Whenever we are getting the plus sign, we are adding the entries to the hash map. When we are getting minus sign, we are just deleting the entries from the hash map. But there is a problem. The problem is that in by portfolio hash map, we need to traverse the complete hash map in order to determine the counterparty, right? Because if you see the log file here, when we are performing some delete operation, we are doing using the counterparty. But in case of portfolio table, our key is the portfolio ID, not the counterparty ID. So we need to search the whole table in order to determine which portfolios need to be deleted, right? So we need to traverse the complete hash map in order to determine the counterparty. And so what could be the solution of this? Can anyone say that?
So you can use the counterparty hash map to find the portfolios and check only their
Yeah.
portfolios.
Yeah. That is true. So what we are doing whenever we are traversing the counterparty hash map, we are just getting the portfolio IDs and inserting in a list. And then for when we are deleting from the portfolio hash map, we are deleting the portfolio side IDs which are in the list. This is the solution. This could be the solution.
So
the
can you
basics.
explain the part once again?
Yeah.
Means-
Obviously. So you got a problem, right? So what is the problem when we are traversing through the portfolio hash map? The problem is that when we are deleting some entry here, if you see that. So when we are deleting by counterparty ID, right? So this 45 denotes the counterparty ID, but we don't have any portfolio number associated to it. But if you see the portfolio table here, the portfolio table here, the keys are the portfolio numbers, not the counterparty ID. So the counterparty IDs like 45, which was in the example, could be somewhere in this nodes. So we have to check all those nodes in order to ensure that 45 is there or not, and then we have to delete. Is that understood?
Yes, sir.
Sir, why do we need the portfolio map? I mean, we never use it for these transactions.
I didn't get your question. Can you repeat it again?
Either for inserting or deleting, we finally need the number of portfolios, right?
Yeah, number of unique portfolios, and we have to print the hash map also.
Okay, sir. I got it.
So is the problem is clear, right? So then the solution I can say. So the
So is it
solution is
okay
that if your
Sir?
voice is breaking. Yeah.
Sir, is it okay if we make the portfolio map at the end of the program?
Means should I use only one hash map, you are saying, right?
Yeah, and while printing at the end, we can make it from the counterparty hash map.
But in that case, there is a problem, and we got the problem, right? The problem is that if we have only portfolio hash map, then we have to traverse the complete hash map in order to determine the counterparty, right?
Yes,
So
sir, we'll
our
keep only counterparty hash map, and we'll make
by
the portfolio.
counterparty, yeah, obviously we shall discuss about that later. Okay, we shall discuss in this tutorial also. Now for the time being, just assume we have two hash maps because this is one of the tasks which was given in the assignment. So that's why I'm discussing this first. Okay. So the thing is that the solution is that we just store whenever we are deleting the counterparty hash map, we are just storing all the portfolios in a list tail, and then finally when we're traversing the portfolio hash map, we are deleting all those IDs which are in the list. Now the basic structure could be like this. So here we need two structure. One is hash node, the node structure of the hash per entry. So it would contain key and value, and then a next pointer. So you may keep only key value, but I prefer to keep key and value separately, and because it is more generic while doing other kind of implementation. If you don't need value, you can make key and value is equal to same. Okay. And next we need hash table. So here we need the size of the hash table and the hash array for storing all the entries. So that is of type hash node. Now the initialization is kind of that. So here what we are doing, we are just initializing the hash table, and finally we are initializing the size of the hash table, and then for yeah. Yes.
Yes, sir. Can you go to the previous slide once again?
Yeah, obviously.
Okay, sir. Like just to know the key.
Okay. So here I'm defining the hash table using dynamic memory allocation, and then finally for with the size of the hash table, I'm just iterating through it and then setting all the values to null. That is the initialization for the hash table. And while doing the insertion, I'm taking the hash table, the key, and the value. So first I'm determining the hash value. Hash value can be gotten as explained in the paper, key modulo the hash table size. And then finally we are initializing a new node, and we are putting the values, key and values to the particular field. And then finally we are just adding node to that particular location. And deletion, when we are deleting the hash node, we are taking the hash table and the key, because here we don't need value, right? Because when we're deleting, we are deleting using a key. So we are getting the hash from there, and then we are creating another node, and we are locating that node which needs to be deleted. And then finally we are freeing that particular node, and then we are setting the value to null.
Sir, here if two counterparties have the same hash value, how are we handling that?
If two counterparties have the same hash values, then we are inserting them as a list, means as a linked list.
Sir, but the linked list is for the portfolios, right? So how are we doing for counterparty?
Means what you are saying means you are saying that the two counterparties have the same IDs.
Sir, I'm saying that if the counterparty is having multiple portfolios, that is what is the linked list is for, right?
Yes.
But I'm saying if two counterparties are at the same hash value, then what will we do?
If two counterparty ID is unique, right? So two counterparty may not be the
Their
same.
hash value, yes, counterparty ID, but sir, hash value can be the same, right? Because we are doing modulo this size.
In that case,
so
what we can, yeah. In that
Sir,
case, what we can, yeah. What is your question?
Sir, if the IDs are 15 and 22, then won't the deletion of only 15 also cause the deletion of 22 as well?
Yes, when we delete 15, then 22 will be deleted in case of by counterparty hash map. In case of portfolio hash map, this will not be the case, right? That you understand.
Yes, sir.
Okay. So in that case, we shall map them to the same location, and as we are maintaining the key and value, that won't be a problem. Means when we're checking the key as well as values, so that won't be a problem.
Okay, sir. So we will check if the value is equal to 15 or not.
Yeah.
Okay, sir.
Someone did the previous question. I'm giving that answer also. So as we are checking the key and value as well, so that won't be a problem. Okay. So now the thing is that we have to read the input file. So say I'm taking the file name, I'm opening the file, and then I'm doing what? I'm initializing the hash table, which was done in the previous slide, and finally I'm just reading the file up to the end, and then if there is a plus sign, then I'm reading in this format, just like that. And when there is minus format, I'm just reading x1 values, and then finally we are returning the hash table. So that's how we are reading all the entries in the from the log file. Is it okay?
So I still didn't understand how will we handle two counterparties with the same hash value.
Yeah, I gave you your answer, right? So if we have two counterparties with the same hash value, then we shall map to the same location with a linked list. And when we are deleting some node, we can check the key and value as well. Hence, we are not checking only the value. We check the key and the value. If there is a perfect match, then we delete. Otherwise, we won't.
Okay, sir. So each node of the linked list is also containing what
Key and value.
counterparty it is coming from.
Yes, yes, obviously. That's why
Okay,
I
sir.
said,
Okay.
because each node has node contains the key and the value, right?
Okay, sir. I got it.
Yeah. So is this clear, the input reading? If it
Sir,
is clear, then we can move on. Yeah, obviously.
sir, while creating the hash table means we are creating it by counterparty ID or by portfolio ID?
Both actually. So we
So
are creating
insert
both.
hash node does both of them.
Yeah, like this. Both actually. One by portfolio and one by counterparty.
But we are making only one call to the function. So
which function you are talking about?
sir, insert hash node function while initializing.
Yeah, actually that I have given for, means this is a generic function. So you can use, means in case of insertion, this is a generic function. So you can create two different tables and use the same function. So that is basically key value pair, right?
So means we have two hash tables and we have to do same process for both of them.
Yes, yes, yes. That's why I have taken hash table as the input.
Okay, sir.
Okay, so now we have to write the output in the file. So what I have to do, first I have to open the file, and then for the length of the size of the hash table, I am writing those values. Like if there is no node, means the position is empty, then we are writing -1 -1. If node is there, we are just printing all those node values in that position. And then finally we are closing the file, because our syntax is like this one, right? So first I have to print the index, and then I have to print the key value. If there is no value is found, then we shall print the -1 -1, and that what I did here also. While I am writing, I am first printing the symbol which I have taken as input. So simple symbol can be C or P. C means by counterparty and P means by portfolio. And then I'm taking the hash table as input and file name as input. And then finally I'm printing if that particular position, means we are taking the hash table ith position. So, and if that particular position is null, then we are printing -1 -1. If that is not the case, then we are printing the key and value. Okay. Now question is, what is the problem with this solution? Can anyone say what is the problem with this solution? Am I audible? Hello?
Yes, sir.
Okay, so what is the problem with this solution? Can anyone say? Okay, no problem. So the problem with this solution is chaining. So here we are using the chaining as the collision resolution technique, right? So hence the search time may not be of order of 1 always. So in order to make the search time order of 1, we have to do something. So what could be the solution? What do you think? So do you got the problem? The problem is whenever we are getting a, we have to search also these nodes in order to determine whether the value is there or not. So that is actually the chaining. So hence the search time is increasing. So we have to do something so that the search time is always order of 1. So what could be the solution for that?
Sir,
yeah,
I had one doubt, sir. When we delete, and we first go to the counterparty map and find the list of portfolios which are corresponding to that counterparty.
Yes.
And then we go to the portfolio map and we check only for those portfolios in which that counterparty is present. But we have to traverse the entire linked list, right?
No, we don't. Yeah, in that case we have to traverse
the portfolio. We have to traverse the entire linked list till we.
Yeah. That is the problem. That's why I'm saying. That's what I'm saying. So we are implementing the collision resolution as chaining, And in case of chaining, the problem is we have to traverse each and every linked list in order to determine whether the value is there or not. So which may not give the solution to be order of 1. So my question is now, what could be the solution so that we can get the values order of 1 time?
So can we use double hashing and then for each double hash value we use chaining for portfolios?
How? Can you tell me?
For example, 3005 and 101 both have a portfolio of 4550. So we like if there is a collision, then we place them in separate hash indices, and then for each index we just make a list. In that way, we only need to delete the head of the list to get rid of the entire list.
Yeah, actually you are trying to say that we have to maintain another hash map for every index position, right? So as this is one hash map and there should be another hash map like this, so that we can locate every element in order of 1 time. Yeah, that is the solution actually. So you have to use the multi-level hashing. So each element in the hash set. Now here the multi-level hashing is basically the hash set. So each element in the hash set, the hash set concept is like that. Each element in the hash set can be searched in order of 1 time. So how to implement the hash set? As you said, for each index of the hash map, we create another hash map. And that way we can create the hash set. The visual demonstration could be like this. So then by portfolio hash map will be like this, and by counterparty hash map will be like this. So here if you see, the total length of the hash table is 7, right? So now 4550 is the key which goes to, if we do the 4550 modulo 7, we get the value 0, and that's why it is here. And similarly, if we see any entry, say 101, okay, so if we do 101 modulo, because here the length is also 7, and if we do 101 modulo 7, we can get the index 3. So by getting 2 index, we can locate a particular element in order of 1 time space. So is it clear to everyone?
Yes, sir.
Yeah. Okay.
Sir,
Yes.
sir, what will happen if we have a collision in the second hash map? Like here in the first row, there is entries 3005 and 101. What will happen if we have an entry whose modulo 7 is 3, like 101?
Actually, in this problem, we are considering that the portfolio and the counter ID means the combination of that should be unique, or the modulo combination of that should be unique. So there will be no such collision, as you were saying. If there is such collision, then we can implement linear probing, that is like this. But in that case, the complexity will increase, or we may simply overwrite the previous transaction. In that case, we may lose the transaction. But in this particular problem, we are considering there is no such case will arise like this.
Okay, sir.
Okay. So the basic structure should be like this. So we need a hash node. So the structure is similar to the previous one. Previously we have key, value, and there is a node, link. But in that case, we don't need any link, right? And the hash table will be same to the previous one. Now the initialization will be a little bit different. Actually, we are defining the hash table first. Then for every table entry here, you can say every table entry we are defining another thing. So actually what we are doing, we are actually defining an array which is table that is a 2D array, so dynamically. So that's why it looks like this. And in the next stage, we are initializing the key and values of every entry position to -1. and then finally we're returning the hash table. Now insertion is like this. So we are taking the hash table, we are taking the key, we are taking the value, and first from the key we are getting the hash index. So previously we are based on the key we are getting the hash index, we are not considering value, but here also for the value we are getting the hash index 2, which is the second hash index. And now for each hash index and hash index 2 position of the table, we are setting the key and value with the respective key and value. That is the insertion. And deletion is we are taking the hash table, we are taking the key, because value is not required. We have to delete every value of that with that particular key, so that's why value is not required. So we are taking a hash table index and we are taking the key, then we are iterating to the hash table size, and then finally when we are getting we are setting the values to -1 that means just the deletion. So you can think the solution as the 2D array, and we are maintaining the rows are basically one hash table and columns are basically another hash table. So you can get the complete code at this link, so you can visit and see the complete code with the input and output, everything is there. Problems, the complete problem was there also, and you can go through that. Okay, now is it understood? Then we can proceed to the next slides.
Yes, sir.
Okay. So the thing is that now as you were saying that can it be solved using only one hash map or hash set? So if so, then which hash map should we use? What should be the answer? Hello?
The counterparty hash map.
The counterparty.
Yeah, by counterparty hash map. But you see, so the answer is yes, by counterparty hash map, that is fine. But in that case, after getting the output, we need to find out the unique portfolios, right? So when we are given a list, if we have to find the unique numbers in that particular list, it could take order of n square time complexity. So how can we overcome that? Okay. Right, you got the problem. For every if I gave you a list with some numbers and you have to find the unique elements, then if you want to do it iteratively, then it should take order of n square time, provided you are not taking any extra space. So how can we overcome that?
Sir, we can then make another hash map on the portfolio values, and then on getting the same portfolio value twice, then we just ignore this.
Yeah, that is the thing. Yeah. Then what should be the size of that hash map? In that case, what should be the size? Means can you say
Sir,
any
at
upper bound?
least,
At least?
sir, at least the number of distinct portfolios.
Yeah, that I know, but actually that solution is not available to me in the beginning, right? So we have to
So at least
design.
equal to the number
Yeah.
of distinct counterparties.
Yeah, theoretically that is true, but practically we have to define first an array, right, with some fixed
Number
length.
of test cases.
Number of test cases. Yeah, that is the actual answer. So in that case, our complexity also remains the number of test cases. If we take the number of test cases as n, then complexity will be order of n. And what could be the other solution? Can you imagine any other solution for solving this problem without doing any kind of hashing operation or kind
So
of
we
that?
sort the portfolios and then we just ignore the duplicates.
We sort the portfolios, then we can, that time complexity will be order of n log n. We want to get some solution in order of n, because up to this point we have seen all the solutions we are getting for order of n time complexity. So we want some solution which is giving the solution in order of n, where n is the number of test cases actually. Any better solution or any other solution? Okay, no problem. So the solution could be like this. We shall take a set which is initially empty, and we shall take a dictionary which is initially empty, and then we traverse through the log file from bottom to up. And if you get -1, then you just set that position, the counterparty position, to true. And if you get plus, you are if counterparty is in L, then you don't have to do anything, right? Because you got the minus in the first place for that particular counterparty. Else you should add the portfolio to the set. And finally you should return S as the set of all existing portfolios, unique portfolios. So that could be one solution. So we are practically here what we are doing, in the previous example we are inserting and then finally deleting, and that's how we are finally making our solution. But here we are not inserting when it has to be deleted. So that's why we traversing from bottom to up. So when we check that it is already deleted, then there is no point to insert that again. We are inserting only those points which are actually there, actually should be there after the completion of all the transactions.
So, but this will work only if we do not insert after deletion. Like in the beginning, there were test cases where we were.
This one you were talking about, I think. This one, right?
Yes, sir. This 45. After deleting 45, we are again inserting. So
yeah, that should not be a problem, right? Yeah, that
no, sir. Here we are assuming that after. Sir, after deleting, if we never insert, only then this one will work, right? The set one.
What will be the problem? Because we are traversing from bottom to top, right? So when we get 45, we shall insert 67, and then when we are getting minus 45, okay, then we are setting that true.
Yes, sir. Okay, I got it. Yes, sir.
That won't be a problem in that case. So we are inserting only those values which will not be deleted in future. So that's why we are starting from the bottom.
So can you repeat this again? If we get minus 45, then what shall we do with the below 45?
Actually, see the insight. Don't go by the algorithm. The insight is that we shall insert only those transactions which will never be deleted in the future. Okay. Now the question is, what is future and how to determine the future? Now the future is the last transaction, means this is the latest transaction which we got. So we should move from bottom to up. So when we are getting some transaction at some point with minus values, then all the previous transactions with this particular ID should not be inserted, right? So suppose here in this point, if we see that is 45 is there with plus value. So when we are getting 45 with plus value, we are inserting the portfolio in the set. So 67 is already there in the set. And now when we are getting 45 again, we are making the flag true. And from now onwards, I shall not insert any 45 further. Is that clear?
Yes, sir.
Sir, I had another doubt. Sir, could you please go to the last slide which you were explaining?
Sorry, this one. Yeah.
Yes, sir. Here you have written that S equals S union portfolio.
Yeah.
So how do we do this union operation in constant time? So we need
actually we shall. Yeah. Say.
Sir, we
I think you can solve this. No, you can solve this. Means we have already solved this previously, right? So we can maintain an array of number of unique portfolios or number of total transactions, and if it is already there, then we shall put them as true, and we shall not insert that again. Like this, what we have done previously where it was. I think we discussed about that previously, right? So what we have to do in that case, we should have to take the array of size, the number of transactions, and if the portfolio is already there, then we shall make the flag true, and so that way we can make it in constant time, means linear time.
Sir, but that requires us to have a previously known value for the upper bound of portfolio.
Actually, number of portfolios are number of transactions. The maximum that many number of portfolios could be there.
Yes, sir, but in that case, we are not being able to avoid another hash map, right? So we need to use another hash map.
Yeah, that is true.
Yes, sir.
That is true. You have to, means literally we are also using the hash map. Yeah, that what I was expecting. Yeah, that is true. Similarly, when if you just see this previously, I am using here dictionary operation, right? So how dictionary operation is maintained? Means here I am giving that at that particular counterparty we are setting the value to true, right? But then in that case, if I have to maintain it using an array, then I have to maintain a huge array. But in case of dictionary, I am doing this. So basically, in case of dictionary, also I am using the hash map. But the
Yes.
data structure is different. If some programming language can give you this kind of support, like Python, you can get the support of dictionary and set. So there you can use this. Means instead of designing all those hash maps and all these hash sets, you can use this to solve this problem very easy way. Okay, so that's it from my side. Thank you everyone. If you have any question, you can also mail me. My email ID is this one. And if you have any more question, I can address that also.
Thank you, sir.
Okay.
Sir, can you send some practice problems for hash tables?
That I can give, but after the exam, I think. You can solve. There are many problems actually available. You can go through the Geeks for Geeks.
No,
That
sir,
is a very
the
good
ones
site.
for the beginner level ones.
In Geeks for Geeks, there are different types of problems and with different levels, beginners, intermediate, advanced. So you can go through that. That will give. And in the meantime, if I can get some beginner level references, then obviously I shall share that with you. But most probably I shall share that with you after the exam. Okay. And in the meantime, you can visit this one. So here you can get the complete code of that. But I have implemented only one table. But the idea is very simple. You can go there and you can get you can design two different tables. I have solved the problem using one table. So here you can get this is the input and this is the output which we are getting. I have shown for one table only, so I'm doing this using counterparty. So that's why every entry is C, and that are the solutions. And this program, this solution has said is basically the efficient way, which we discussed as the second solution. And the previous solution is this one. Yeah, the hash table, solution hash table. So this is the previous solution. You can go through that out, and these are very intuitive in nature. So, and if you need the problem, then the problem is also here. You can go to this link and you can get the problem. Okay then, thank you.
Thank you, sir.
Thank you, sir.
So, is Sad is there or not? Sad is there or not? He left. Can anyone say Sad is there or not?
I think he's in there, sir.
Oh, he's not here, right? So then shall I leave?
So stop recording. Please stop the recording.
Okay. Thank you.